The Earth's core is a place of unimaginable heat and pressure, where no life can survive. Yet its existence is crucial to life on Earth. Rapidly advancing science reveals the Earth's center as the powerhouse that drives our planet. The core is a mammoth, violent generator. Thousands of miles below us, liquid metal, hot as the surface of the sun, surges and swirls in giant currents that generate massive amounts of magnetic energy. The magnetic waves created permeate through the Earth and out into space, blanketing the planet in an invisible force field. That's all that stands between us and the lethal radiation of space. But that generator may be losing steam. New discoveries from the Earth's core show signs of cooling, signs that our planet's heart may be slowing down. One day, the Earth could lose its magnetic field and become a barren wasteland, just like Mars. Scientists think when Mars's core died, so did the rest of the planet.
The reactor might die in 100 years from now, maybe 1,000.
The Earth is decaying.
Naked Science is making an imaginary journey to the heart of our world to answer the ultimate question: what lies at the Earth's core? We have navigated the oceans, climbed the highest mountains, even walked on the moon, and made a new home for ourselves in space. But when it comes to what lies beneath our feet, we have barely begun to scratch the surface. Underneath us, over 99% of our planet remains unexplored.
Our very own planet is still a mystery to us.
The interior of our own planet is so inaccessible to exploration, and yet we can explore the very depths of our universe and see back to shortly after the Big Bang that created the universe.
If you have ever dreamed of journeying to the center of the Earth, don't hold your breath. It's almost 4,000 miles below us, roughly the distance from Chicago to London. But in this scenario, nobody has even left the suburbs. The deepest ever caving expedition extended to a depth of just over a mile. Thousands of caves remain unexplored to this day. The deepest mines in the world are the Western Deep Levels gold mines in South Africa. They descend 2.3 miles into the Earth, where the temperature is a sweltering 130 degrees Fahrenheit, heated by warm rocks below. With a shaft so deep, the miners have to descend in several stages. The deepest hole ever drilled is here at Kola in Russia. It extends 7.5 miles down. This drill is so long, it distorts like a piece of elastic. But even the deepest drilled hole is still some 3,955 miles short of the center of the Earth. Barely a pinprick on the surface of our planet. The Earth is like an onion, made up of different layers of material. The crust is a thin layer of rock, a few tens of miles thick. The largest region of the Earth's interior is called the mantle. It's almost 1,800 miles of putty-like rock. But beneath the mantle, the core is roughly the size of the moon and is made up of two parts, the liquid metal outer core and the solid metal inner core. This is our deep Earth destination as we begin our mission to find out what lies at the heart of our planet. Naked Science is on a quest to examine the latest scientific thinking at each layer of the Earth, eventually arriving at the very center. But it's a long way down. To get an idea of the true scale of the task, imagine a skydiver dropping towards the Earth from 10,000 feet up. He would fall so fast, he would hit the ground in 1 minute. But imagine if there was a tunnel all the way to the core. How long would it take him to fall to the center of the Earth? The Earth is so huge that a fictional skydive to the very center of the planet would take a staggering 32 hours. We're going to follow him on his one-way ticket through each layer. As he plunges into our imaginary tunnel, after 3.5 minutes, our skydiver would already have dropped further than the deepest hole ever drilled. 20 minutes later, he would reach the bottom of the first onion layer of our planet, the Earth's crust, 43 miles thick at its deepest point. He would then enter an enormous region of hot putty-like rock, the mantle. The mantle is almost 1,800 miles thick, about the distance from Chicago to LA. It would take our skydiver over 15 hours to fall through it. Of course, a skydiver free-falling through the Earth is pure fiction. In reality, the human body would be unable to survive deeper than a few miles beneath the surface. But why? It's to do with the conditions within. The Earth's interior is extremely hot and massively pressurized. In fact, current estimates put the temperature right at the center of the Earth at between 9 and 12,000 degrees Fahrenheit, about the temperature of the surface of the Sun. But where has all this heat come from? 4.5 billion years ago, when our solar system was born, our planet was subject to a series of catastrophic impacts. The collisions generated so much heat that the entire planet melted. With time, the Earth cooled off, and the outer layers hardened into rock. But rock is a good insulator, and most of the heat remained locked inside, supplemented by extra heat from radioactive elements. But it's not only the scorching temperatures that are a barrier to exploration. It's also the crushing pressures. With the weight of the world bearing down on it, the pressure at the center of the Earth is 3.6 million times that at the surface. This Naked Science demonstration shows how poorly equipped the human body is to deal with such high pressures. A watermelon has roughly the same density as a human head. In this demonstration, a bullet flying through the air at over 3,000 miles per hour generates a pressure of more than 3 million pounds per square inch. The pressure at the Earth's core is a staggering 51 million pounds per square inch. The equivalent of 15 bullets hitting simultaneously. But with this kind of pressure all around you, your head wouldn't explode, it would implode. In fact, it takes specially constructed guns like this one at Caltech in Los Angeles to recreate the same pressure you'd experience at the core. Earth scientists use it to test materials under millions of atmospheres of pressure.
Firing key in, and fire.
At Berkeley, scientists go one step further. They can test materials under extreme pressures and sun-like temperatures in a machine called a diamond anvil.
So quite literally, we squeeze on a sample material between the tips of the two diamonds, achieving extremely high pressures.
Diamond is the hardest substance on Earth. These are just plastic models. The real ones are much, much smaller. Not only does the machine squeeze, it also heats, shining powerful lasers through the diamonds. And using diamonds has an added advantage. They're transparent and can act as windows on the material.
And so we can actually look at that sample while it's at the high pressures and high temperatures that exist deep inside the Earth.
The high-velocity gun and the diamond anvil are among the only ways we have of creating core-like conditions on the surface of the Earth. Could the materials developed within them one day form the basis of a machine that will get to the core? Humans may never be able to travel there, but could we build a remote probe that may feed us information about what lies beneath? We are proud of our ability to push back the frontiers of our domain. But our own backyard is the toughest frontier of all. Our planet has a violent interior that's completely inaccessible to exploration. Until now, we've only managed to dig barely 8 miles down. But one man has an outrageous idea to blow that record out of the water.
Many of my scientific colleagues, upon seeing this idea, laughed.
Caltech's Dave Stevenson has a revolutionary idea that he is convinced will work, if someone is willing to foot the bill.
Perhaps $10 billion. I'm just making a guess.
His idea is striking in its brutal simplicity.
You start a crack in the Earth, which then propagates rapidly, just as when you hit a plane of glass with a hammer, the cracks move so fast that you can't even see them with your eye.
The hammer, in Stephenson's plan, would have to exert as much energy as a magnitude 7 earthquake. He suggests using atomic warheads. The next step would be to pour molten iron into the crack, and lots of it.
That volume is equivalent to the amount of iron in about 100 Eiffel Towers.
Stephenson believes that this much iron would sink like an upside-down lava lamp all the way to the core. Inside it, a probe made from materials developed in diamond anvils and pressure guns would read data from its surroundings, communicating back to the surface using waves of energy. It would reach the core within a week and then be lost forever. But in the process, it could provide us with new data about the makeup of the Earth's interior and the future of our planet. It may be simple, but in this demonstration, Stephenson attempts his own idea on a somewhat smaller scale.
What we have here is the mantle of the Earth represented by jello, and we have the liquid iron here represented by corn syrup. And what I expect to have happen is that it will sink down through the jello to the bottom, just as the material would sink to the Earth's core.
Stephenson uses a dessert spoon in place of the nuclear bomb.
And there it goes, sinking down through the jello to the bottom of the mantle.
Like the mantle, jello behaves like a solid. Like molten iron, corn syrup is a fluid. This shows how it might be possible for a liquid to sink through the mantle.
The other big advantage of this experiment is that once you finish the experiment, you can eat it.
Stephenson's idea is a long way from ever becoming reality. But if it worked, it would break all depth records. Right now, it seems there is no gateway to Hades. If we are ever going to learn about the center of the Earth, we'll have to find another window on the world below. The key to viewing the inner Earth lies in one of the most destructive natural forces we know, forces that allow us to take a snapshot of the core. San Franciscans live on a geological knife edge, under constant threat from the violence that Mother Earth keeps locked beneath us. They know they're already overdue for the big one that is set to devastate their city. Many live in fear, but some, like Ed Garnero of Arizona State University, have a bizarre fascination with quakes.
Earthquakes are incredibly powerful things and sometimes can destroy whole cities. But for seismologists, there's something that we can actually get excited about.
This earthquake simulation at Universal Studios shows what might happen to a subway station during a magnitude 8 earthquake. Earthquakes are the result of what scientists call tectonic activity. The crust isn't a giant single slab of rock. It's broken up into 8 major tectonic plates. They move slowly across the surface of our planet, driven by forces from below. The plates grind against each other, distorting over time. Eventually, they can't stretch anymore, and they violently snap into place. This snap is what we feel on the surface. Earthquakes give proof that the Earth's interior is alive. They also provide a method of viewing our subterranean world. Garnero uses earthquakes to map the inner structure of the planet. Sites like this one are dotted around the globe, unassuming scientific equipment buried into the earth.
That's interesting. Gophers.
Seismometers are like cameras pointing downwards towards the core. But they don't take pictures. They read shock waves from earthquakes on the other side of the world. The waves tell seismologists about the material they have been traveling through. Then, it's a matter of turning the shock waves into pictures of the Earth's interior. The result is very similar to an ultrasound of a baby in a womb. Sonograms use ultrasound to see inside the human body. The waves travel at different speeds through different types of tissue, and the computer interprets them as different shades of gray. To the human eye, it's a picture.
Here's a picture of Nico, and this was actually probably just a couple months ago. Obviously, we're so used to looking at photos, we know exactly what's in it because it's so clear. Anyone could also look at the sonograms from when they're in the womb. If you take them at face value, it's bright spots and dark spots.
The spots are images generated by a computer. The ultrasound machine reads waves reflected from inside the fetus.
So when we do the same thing in seismology, we think we understand some basic principles, and that, along with interpreting sometimes the opaque images, we come up with a model.
Thanks to seismology, we now have a detailed picture of what is beneath our feet. We can see the different layers and know which parts are solid and which are liquid. Below the thin crust, made from the rocks we know at the surface, the 1,800-mile thick mantle is also solid, but in a plastic putty-like form. Now, new seismic studies reveal that there could be a kind of subterranean mountain range near the core mantle boundary. In reality, this Mantle mountain range is far bigger than any mountain on the surface. These are continent-sized features.
Mount Everest would be, slightly a pixel on this plot.
But what are these structures, and what do they do? Although seismologists can see them, nobody understands their true role in the workings of our planet. Could they be acting like giant lava lamp plumes from the deep, providing scientists with material from the base of the mantle? Iceland was made famous as a gateway to the core in Jules Verne's classic tale, Journey to the Center of the Earth. There's no route to the core here, but today it's a popular tourist destination as thousands flock to see volcanic activity. 6,000 miles to the west, the Big Island of Hawaii is equally spectacular. Both islands have been termed hotspots, volcanic areas that are thought to emanate from hot sections of the mantle. But what depth does the hot stuff come from? Among volcanologists, there are two schools of thought. Those who believe that material emerges after a long ascent from the base of the mantle, and those who believe that it originates from the top of the mantle. Volcanologist Ken Hahn runs a demonstration of the two theories.
The idea of a deep hotspot is very similar, in fact, to something that, well, maybe not everybody has, but people my age have seen. It's a lava lamp. Down at the core mantle boundary, there's heat, and that heat escapes from the core and heats the overlying mantle, which becomes lighter, a lot like a helium balloon or something like that, and this material rises up through the mantle of the Earth until it comes up near the surface.
Like most volcanologists, Hahn subscribes to the deep hotspot theory. But a new theory could soon change that scientific opinion. It suggests that the lava we see in Hawaii and Iceland is not generated by heat that has risen from the bottom of the mantle, but the very top, released thanks to a drop in pressure where the crust has cracked. Like Stevenson's Jell-O, Hahn uses cornstarch to illustrate the idea, a material that is very similar to the putty-like mantle.
If I push on the cornstarch here, I can keep it solid. And this would be like what the mantle is underneath the crust.
Although the cornstarch is solid under pressure, just as the mantle is, as soon as the pressure is released, it melts. According to this new theory, Iceland and Hawaii are merely cracks in the crust that have released pressure on the mantle. The result is lava. But what are the implications if the cornstarch theory turns out to be the right one? Gillian Folger is the founder of the theory. She has spent over 25 years in Iceland gathering data to support her idea.
It was really a kind of the sort of eureka moment that you, a scientist like myself, perhaps can only hope to experience maybe 2 or 3 times in your career if you're lucky.
If Folger is right, then hoping to learn something about the core this way could be a blind alley.
Well, the implications are very radical, really, because up until now people have assumed that if you take rock samples from Iceland or Hawaii, then you're basically getting some kind of window into what's happening at the very centre of the Earth, right down at the Earth's core. But this theory, although it's very, very exciting and it's very, very new, for those people who are interested in studying the core, it carries the rather sobering news that these rocks are telling us nothing about the core. They're only telling us about the very shallow Earth.
Whichever theory is correct, Earth scientists still have much to learn from volcanoes. Lava originates from well below any depth we could hope to reach. So far, our Earth diver has traveled 2,000 miles in under 20 hours. Now he is plummeting through the outer core of the Earth. The outer core is a liquid layer of molten iron and nickel. An ironworks is a perfect illustration of what the outer core might be like. Liquid metal flows freely at several thousand degrees Fahrenheit. Here, naked science measured molten iron at 2,500 degrees Fahrenheit. But although it's thousands of miles beneath us, scientists can study the outer core because of the invisible field of energy it produces. We spend our lives immersed in this field, yet we can't see it, hear it, or feel it. But it's all around us. The Earth's magnetic field. For centuries, sailors have known about magnetism and have used it to navigate their way across our world. but they would never have been aware of its significance as our planet's protector. Like electricity, the Earth's magnetic field flows in a circuit. It flows from the Earth via the South Pole in great waves of energy, traveling hundreds of thousands of miles into space before sweeping back into the Earth via the North Pole and returning to the outer core. And it's the core's invisible magnetic force field that makes life possible, protecting us from the deadly radioactivity of space. Most people are aware of the dangers of sunbathing, but without our magnetic field, we could be exposing ourselves to far worse than sunburn. At its center, the sun behaves like a giant nuclear reactor, generating radioactive heat. Enormous storms rage on its surface, flinging radioactive winds into space, some in the direction of Earth. But as the solar winds gust towards the Earth, our magnetic field behaves like a giant umbrella, deflecting charged radioactive particles away from us. At the poles, where the magnetic field flows vertically in and out of the Earth, cosmic radiation enters the atmosphere, glowing brightly in fantastic displays known as the Aurora Borealis at the North Pole and the Aurora Australis at the South Pole. Without our magnetic umbrella, the Earth would be bathed in radiation. But where does the field come from? And how is it generated? Dan Lathrop of the University of Maryland thinks he has the answer.
Earth produces a magnetic field much like a bar magnet or a refrigerator magnet might. The Earth does it, though, by a very different process.
The current theory suggests that the outer core is the Earth's magnetic powerhouse. Within the outer core, billions of trillions of tons of liquid metal constantly circulate like weather systems in our atmosphere. This subterranean ocean of iron and nickel is thought to be the origin of our magnetic field. In this experiment, Lathrop's team have built a model of the Earth's core to test the theory that a ball of liquid metal can generate magnetism.
This is an experimental model of the Earth's core. So the ball, when I'm running the experiment, is filled with the liquid metal, and then we spin the whole thing at high rotation rates up to about 30 revolutions per second.
To melt iron would take too much energy. So in this experiment, they're using sodium. Sodium is a metal and has many of the same properties as iron, but it's much easier to melt, which makes it an ideal substitute. But there is one catch. It's highly reactive. Even small amounts burn explosively in water.
You can go ahead and turn the heaters on, Dan.
The Earth and its core spin just as the sodium ball spins. The motion of the liquid metal inside generates magnetism. Proof that the Earth's outer core can produce a magnetic field.
You see all sorts of complicated motion in the induced magnetic fields. So that the rotating turbulent sodium flows cause oscillations and all sorts of chaotic motion, not unlike the sorts of unpredictable motions one might see in the Earth's atmosphere.
It seems that magnetic fields produced by balls of liquid metal are unstable systems. But just how unstable are they? Scientists now have evidence that the Earth's magnetic shield is losing strength.
The magnetic field at the Earth's surface in this region is considerably weaker than we would expect.
Over the past century, the strength of our field has declined by as much as 10%. And with a weaker field, high-altitude airliners and astronauts in orbit are already being exposed to higher doses of space radiation. Could Bloxham's evidence be the first indication that our field could one day disappear? And what would happen if it disappeared completely? The Earth is enormous. Beneath your feet, it's almost 4,000 miles to the center of the planet. About the distance from New York to Salt Lake City and back. Naked Science is on a mission to the core to investigate the violence and mystery of a world we have never been able to explore, and to investigate signs that we may be witnessing the beginning of the end. Marblehead, Massachusetts. Naked Science is in town to uncover a potentially alarming discovery. In the 1990s, Jeremy Bloxham of Harvard University published data that was widely regarded as the clearest indication yet that the Earth could be in for a turbulent ride.
One of the things I looked at a long time ago was I realized the need to see how the magnetic field has changed, and that meant going to observations of the magnetic field that have been made by people like James Cook during his voyages of exploration.
For centuries, sailors have been keeping a record of the Earth's magnetic field.
Back in the 18th century, people were making careful and methodical observations of the magnetic field so that they could work out the angle between true north and compass north for navigation.
Compass needles are themselves tiny magnets. They work by lining up with the Earth's magnetic field. But the north a compass will point to, known as magnetic north, is not the same place as the north you will find on a map, called true north. Thanks to the motion within the core, magnetic north is constantly on the move. Scientists can predict where it will go in the short term, but its long-term future is anybody's guess. So to help sailors navigate, nautical charts were routinely updated with the angle of deviation, the angle between true north and magnetic north. Today, the charts tell a detailed story about the core. At Harvard, Bloxham has been painstakingly compiling 300 years of data from the archives to produce a movie of the fluctuations around the core since 1690. The red areas indicate the regions where the field flows out of the core. The blue areas are where it re-enters.
One rather striking thing in particular, beneath the Pacific, the field really doesn't change very much, whilst here, beneath the Atlantic, the field is changing much more abruptly. You can see how this patch grows and then drifts towards the west, leading to this large region here beneath the South Atlantic Ocean, where instead of field lines coming out of the core, as we would expect for the southern hemisphere, we've actually got field lines going back into the core.
Known as the South Atlantic Anomaly, the magnetic field in the South Atlantic isn't just weakening, it's flowing the wrong way. Could this be the first indication that the Earth's core is in terminal turmoil? To find out more, Naked Science travels to the middle of the Pacific Ocean. The Big Island of Hawaii is famous for being the largest volcano on the planet. From the sea floor, it's almost twice the height of Everest. Scientists from the U.S. Geological Survey keep a watchful eye on the lava, monitoring when and where it will erupt next. Here, lava flows through underground tubes towards the ocean. As it hits the sea, new land is formed as it rapidly hardens. It's these new lavas that hold the key to our magnetic past.
When lava comes to the surface, it's not very happy. I mean, it comes from a place that's very warm, and so it immediately starts to cool. And as it cools, one of the things that happens is small little minerals start to form inside of the molten rock. And one of those minerals that forms in there is a mineral magnetite.
Like millions of tiny compass needles, the magnetite crystals line up inside the rock, recording the strength and direction of the field at the exact moment it solidifies. Each lava flow tells a story about the field at the time it erupted. The Hawaiian archipelago is like one big 70 million year magnetic database, and its history is astonishing. It seems that the Earth's magnetic field didn't just weaken, it went a whole lot further than that.
In the past, the magnetic field has completely reversed. So the North Pole has become the South Pole and the South Pole the North Pole.
Here was evidence for a total global magnetic reversal, called the flip. And the story doesn't stop there. The field has flipped before, 170 times.
Basically, what this graphic is showing is the polarity of the field. So when it has one polarity, we color it in black, and when it has the opposite polarity, we color it in white.
It's as if the Earth has a barcode. There have been hundreds of flips since the planet was formed. And looking closely at our recent past shows that the Earth may be on the verge of another.
In the last 150 years, we've seen about 10% of the Earth's north-south component destroyed by this process of growth of this reverse flux patch. That's about the rate at which the field changes during a reversal.
This patch of reverse flux over the South Atlantic could be the first indication that the Earth is in the early stages of the next flip.
It seems that it's not a question of if the magnetic field of the Earth is going to reverse, but when the magnetic field is going to reverse.
Nobody has ever experienced the flip. The last time it happened was 780,000 years ago, when Homo erectus walked the Earth. The flip occurs on average once every 200,000 years. We're already overdue by almost 600,000. So what could we expect if we're about to go through one? First, the Earth would develop multiple poles at random locations, north, south, east, and west. We'd see auroras at night all over the planet. But more seriously, we may experience heavy doses of solar radiation that could cause a cancer epidemic. But nobody can be sure. Naked Science's journey to the center of the Earth has revealed subterranean mountains in the mantle and a magnetic storm in the core. And we've learned that the outer core has a vital role to play in preserving life on Earth. But what would happen if the Earth's magnetic field were ever to be turned off? To find the answer to this question, Naked Science launches skyward to another planet entirely.
We have ignition, and we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the Red Planet.
On board the Mars Global Surveyor, magnetic recording equipment beamed back valuable data to Earth. It revealed that there is no magnetic field emanating from Mars's core. But there was a twist in the tale. Within the crust, NASA found strong evidence of a magnetic past. Mario Acuna headed the team.
We saw the instrument record a very large magnetic field by Mars standards over a very small region of the planet.
NASA had made an astonishing discovery. Although there was no field from Mars's core, sections of the crust were strongly magnetic. This can only happen when lava solidifies in the presence of a magnetic field. Just like on Hawaii, solidifying lava on Mars's crust had preserved a record of a magnetic past and a liquid core just like the Earth's.
But it was no longer there. It had disappeared.
With a magnetized crust, but no evidence of a global magnetic field, NASA concluded that at some point in Mars's history, its core had solidified. But what exactly happened to Mars's core? Could the same thing happen to the Earth? To find the answer, we have to dive deeper still through the onion layers of our planet. Our skydiver is now deep inside the liquid metal outer core, 24 hours into his journey. Beneath him, he plummets towards a solid iron and nickel globe, the inner core. Scientists believe that the inner core, although it's hotter than the outer core, is kept solid by crushing pressure. But here's the unusual part. The inner core grows as the Earth cools. In fact, the Earth has been cooling ever since it was formed. The Earth's heart is freezing solid. It may only be a matter of time before the Earth loses its magnetic field, just like Mars. But when might this happen? Could the cooling core be nearing the end of its life?
I mean, there is indications from our measurements throughout the last 50 years that the Earth is decaying, is decreasing rapidly. Some people have projected that maybe in 1,200 years the field would disappear.
But why hasn't the Earth's core already frozen like Mars? Mars is a smaller planet, so it could have cooled more quickly than the Earth. But could there be something else within the Earth's core that's keeping our planet warm? Our skydiver's free fall to the core has already taken him to the limits of mainstream science. After 32 hours, he is now close to the center of the Earth. And if you believe one man, our skydiver could be about to hit one more layer that could explain everything.
In a nutshell, a nuclear reactor at the very center of the Earth.
Maverick scientist Marvin Herndon has been working on this unconventional idea for 30 years.
So I guess what you're really asking me is to tell you how insane I am.
Herndon thinks that within the solid inner core, a 5-mile-wide ball of uranium and plutonium generates the heat that powers the motion of liquid metal in the outer core. Herndon struggles to get his idea recognized. Most scientists think it doesn't add up. But just how crazy is this idea? His arguments are based around meteorites, lumps of rock that occasionally fall to Earth.
It was just a huge explosion, and we looked around and it was just dust everywhere. So unbelievable, really. I'm just glad that no one was sitting on the couch.
Scientists agree that meteorites are the purest material in the solar system, that they're lumps of material left over from the formation of the planets. Herndon believes that there is one type of meteorite, called an enstatite chondrite, whose makeup is more like the Earth's composition than other meteorites. According to his research, the chemical nature of enstatite chondrites could tell us about what's happening inside the Earth.
Well, I did this for almost 200 meteorites, and it's amazing. The enstatite chondrites are the only chondrites that have the kind of percent of alloy that the Earth does.
Enstatite chondrites are laden with uranium that would sink to a planet's core. And while many would disagree, Herndon believes this is what happened when the Earth was formed. He reasons that there's enough uranium and plutonium at the core to spontaneously react. If that sounds far-fetched, no one has explained this peculiar fact. Jupiter radiates twice as much energy as it receives from the Sun. Like Herndon's Earth, Could Jupiter's stormy gaseous facade hide a planetary-scale nuclear reactor? Then there's a small region of West Africa called Oklo. In the 1970s, French scientists revealed that this uranium mine was once a natural fission reactor.
That was proof that in nature there can be nuclear reactors. Well, all of a sudden, the pieces just all came together at once.
But the true cornerstone to the Herndon theory lies in one particular chemical that emanates from hotspot volcanoes like Iceland and Hawaii, a form of helium.
Now, when uranium fissions, it splits into two pieces, helium of mass 3 and helium of mass 4. And these are the fission products.
The fission products are like fingerprints of a nuclear reaction. Herndon argues against prevailing opinion that the helium that erupts within the lavas can best be explained by his nuclear reactor theory. He thinks the reaction byproducts are swept to the surface by hotspot plumes. So if he is right, what are the consequences? His most recent calculations show an alarming trend. They show all the signs of a nuclear reactor that's running low on the fuel that powers it, uranium.
The reactor might die in 100 years from now, maybe 1,000, maybe 1,000,000 years from now, and perhaps even 1,000,000,000 years from now. We just can't say with any certainty on that.
Herndon believes if the reactor dies, so will the magnetic field. But whether there is a nuclear reactor at the core or not, all scientists agree that one day it will freeze solid. It's just a matter of time. So what would happen to a planet that lost its magnetic field entirely? Could the loss of Mars's field be linked to the time it became a lifeless desert? The answer lies in the discovery on Mars of two of the biggest impact craters in the solar system, thousands of miles across. Hellas and Argyre, left behind after asteroids collided with the planet. NASA found no evidence of magnetized rock within these craters. When they were formed less than 4 billion years ago, Mars's core had already stopped producing a magnetic field. NASA believes that this is the time that Mars started to lose virtually all of its atmosphere and oceans. Over billions of years, the planet was stripped of its atmosphere, unprotected from waves of cosmic radiation. The barren red planet we know so well today was all that was left.
We see Mars, we thought it was a cousin of Earth, but this is a cousin that aged very fast. Things that happen on Mars. Mars is a desert. Can it happen on Earth? It certainly can.
Naked Science set out to find what is at the center of our planet. We may never get there, and we're still some way away from finding out what is really beneath us. But modern science has unearthed a vast wilderness, yet to be fully explored. Our own backyard is the true final frontier. But one thing is clear. The Earth's core is crucial to the continued survival of our world. Without the protective magnetic shield it generates, our planet would be open to a radioactive onslaught from space. The Earth could one day become a desolate wasteland, just like our red neighbor.